Okay, so let's take a look at one more problem. Let's imagine that we have our coordinate system here, and at the origin, let's put a charge of positive 6 microcoulombs, and then at the point 2 meters, let's put a charge of negative 3 microcoulombs, and let's figure out what is the total potential at the point 4 meters. So the question is then, what is the potential at 4 meters? So we've got two charges. The total potential will be the potential due to the charge at the origin plus the potential due to the charge at 2 meters. So what's the total? Well, we can do this all in one equation. V is equal to the potential due to the 6 microcoulomb charge will be kq over r, 8.99 times 10 to the 9th Newton meter squared per coulomb squared, times q, or 6 times 10 to the minus 6 coulombs, over r. R, in this case, the distance from this charge to this point, 4 meters, plus the potential due to this charge, which will be kq over r, 8.99 times 10 to the 9th Newton meter squared per coulomb squared, times q. Q in this case is minus 3 microcoulombs, minus 3 times 10 to the negative 6 coulombs over r. R for this charge is going to be this distance from 2 meters to 4 meters, which is just 2 meters. 2 meters. Okay, there we go. So let's combine these. This term, we get 1.35 times 10 to the 4th volts. Over here, we're going to have minus, multiply that out, and what do we get? 1.35 times 10 to the 4 volts. So we get 1.35 times 10 to the 4 volts minus 1.35 times 10 to the 4 volts. What do we get? We get 0. The total potential at this point is 0. We find the potential due to this, which is essentially going to be proportional to 6 over 2, is then canceled by the potential, which is essentially minus 3 over 4, so we end up getting the same thing, and they cancel out. Now, physically, what is going on here? How does that make sense? How is it possible for the potential at some point here to be 0? Well, let's think about actually bringing a test charge in from infinity. Using these two results, kq over r, means we have set the potential to be 0 at infinity, so how is it possible to be 0 here? Let's imagine we have some positive test charge and we want to bring it in from infinity. How do we end up actually doing no work to get it to this point? Well, when we're very, very far away, like the examples we did when we were looking at the field drawings, we're going to have basically a plus 6 and a minus 3 coulomb charge very close together. They're essentially going to partially cancel each other out and give rise to a positive 3 microcoulomb charge. So very far away, that's going to look like a positive charge. So bringing in a positive test charge from far away, we're going to have to do work pushing this in. We have to push the positive charge in. We're increasing the potential energy. However, as we start getting close to the minus 3 charge, the difference in distance between these two will start to become noticeable. We're actually going to be closer to the negative charge, further from the positive charge. The negative charge is going to start to dominate the force, and eventually the force is going to be attractive on the positive charge, and we're going to actually have to do negative work to bring it in. The force actually acting on the charge acting on the test charge from these charges will be attractive. And so for part of the way, we're going to do negative work. Well, it turns out that when we get to the point x equals 4, the amount of positive work we've done is going to be exactly canceled by the negative work we've done to give rise to a total work of 0 when we get to the point x equals 4. To be a little more specific, when we're very far away, the electric field is going to point away from the charges. And it's going to point away increasing. That electric field is going to increase as we get closer until we get to the point 9.69 meters. And that's where the electric field is going to have a maximum value. It's going to point away from the charges with the greatest electric field. In other words, the force acting on the test charge will be the maximum pointing to the right that it's going to be. As we continue to get closer, eventually at the point 6.83 meters, that's where the electric field is actually going to be 0. So if you calculate the electric field at the point 6.83 meters, these two electric fields will exactly cancel out. Essentially, that's where Q over R squared for each of them will have the same magnitude. One repulsive, one attractive, and they will cancel out. And then if you continue to move in, then the electric field is going to point to the left. The force acting on the charge will be toward the charges. So, essentially, the work that you do from infinity to x equals 6.83 will be positive because you're working against the electric field. Then, from 6.83 to 4.0, the work that you do moving inwards will be negative, and essentially the work that you do on this side will exactly cancel out the work you do on this side, so that the total work by the time you get to 4 meters will be 0. So it's kind of a very surprising result, something we might not have expected, but once we stick the numbers in, that's what we find. Okay, let's stick in just a few numbers one more time, one quick calculation. When dealing with batteries, you will often see the voltage of a battery exactly listed right on the battery. For example, this is a D battery, standard D-size battery, D cell, and you can see on it it says 1.5 volts. That means that the potential difference, or the voltage between the two terminals, is 1.5 volts. This is a 9-volt battery, and a 9-volt battery means the potential difference between the two terminals is 9 volts. A standard potential for a car battery is about 12 volts. So let's imagine that we've got a 12-volt car battery. A reasonable charge that a battery will deliver before being completely discharged. So imagine that your car is not recharging the battery. You allow it to completely discharge itself. It will give off, say, about 7.5 times 10 to the 5th coulombs. So let's figure out how much energy that corresponds to. So imagine we have a car battery. We've got terminals here. The potential difference between the two terminals is 12 volts. We move a charge of 7.5 times 10 to the 5th coulombs from one terminal to the other. How much energy is that? Well, the total energy, the potential energy change due to the motion of those charges will be voltage, or it's going to be Q delta V, a charge of 7.5 times 10 to the 5th coulombs. We're going from the positive terminal to the negative terminal, so we've got a change in voltage of negative 12 volts. So multiply that out. How much energy have we lost? That's going to be about 9.0 times 10 to the 6th joules negative. In other words, those charges have lost an amount of potential energy of about 9 million joules. In other words, they have delivered that energy to the circuit. We're getting an amount of energy of 9 million joules out of this electrical circuit. So let's just try and figure out how much could we do with this much energy. Well, if we could imagine taking, say, a 10 kilogram mass, so a mass, a block of metal or something, say 10 kilograms, that would be about 22 pounds. This amount of energy would raise this mass to a height of 91.8 kilometers. So if we could take all of that energy, without losing any of it, it would raise 10 kilograms to a height of 91.8 kilometers. That's a very, very large height, kind of surprising. So it just kind of demonstrates the kind of energies we're talking about with, well, say a car battery in this case. All right, so very, very good. Next time, we'll take another look. We'll keep looking at potentials. We'll look at another way of interpreting what these potentials mean, and we'll also take more of a look at capacitors and how we can use those.